All right, so let's start today by reviewing a little bit of empirical molecular formulas. And we're going to get into it here by looking at a problem where we need to deal with both the empirical formula and the molecular formula. And so here we are told that the mineral magnetite is found in bird beaks, and it may be thought to be one of the reasons how birds can navigate their direction. Magnetite is an oxide of iron. It is 72.36% iron by mass. What we want to know is, what is the empirical formula? So what we need to do first and foremost is we need to look at this and again break it down into our percentages. So we are told this is 72.36% iron. Now, since this is an iron oxide, we know that the other component of this has to be oxygen, as has been the case for our other two examples thus far. And so if it's 72.36% iron, then the remainder, so 100 minus 72.36, would be 27.64% oxygen. Now, if you remember our process, we go from percents to grams, grams to moles, to finally the molar ratios. So starting with our percents, we're going to turn them into grams. 72.36 grams of iron. And we're going to turn it into moles using its molar mass. 55.85 grams of iron in every 1 mole of iron. 72.36 divided by 55.85. Do 4 significant figures, 1.296 moles of iron. Now, that's only one part of this. The other part is the oxygen. So I can start with the 27.64 grams of oxygen. Turn that into moles by dividing by its molar mass. So 27.64 divided by the molar mass of oxygen, which is 16. 1.728 moles of oxygen. So once again, just like in our example on Friday, we have a ratio of elements that is not clear as to what it is. And so when we don't have a clear-cut example of, oh, these two are the same, it's 1-to-1. This is clearly double the other. Then what we need to do is to determine the mole ratios, we need to divide by the lowest number, which in this case would be 1.296. When we do that, that guarantees that we have 1 for the iron. And if we take that 1.728 and divide by 1.296, we get 1.333 oxygen. Now, you saw something similar to this in your post lecture. Now, we didn't cover explicitly what to do in lecture on Friday, but it was kind of implied. So if you struggled with this, you missed the connection. That's okay. We're going to cover that connection right now. And the connection is this. If the numbers do not come out to be whole, there's a very good chance that they're going to be fractional. Now, in the example on Friday, we had 1 and 1.5. So when we do get rid of 1.5, well, we got rid of the half, we're multiplying by its denominator, which is 2. Now turn the 1.5 into 3 and the 1 into 2. Well, in this case, 0.333, that's a fraction as well. That would be a fraction 1/3. So if I have 1/3 as my fraction, I need to multiply by 3 to get rid of that fraction. So I'm going to multiply each of these by 3 to get rid of those fractions. I'm going to end up with 3 iron. And I'm going to end up with 3 times 1 1/3, which would be 4 oxygen. So Fe3O4 is going to be my empirical formula. Now to do this second part, remember I'm trying to solve for the multiplier. The multiplier is the molar mass divided by the empirical mass. And what that multiplier gives us is it's going to tell us what number we need to multiply our empirical formula by to get our molecular formula. So the molar mass is 231.5 grams per mole. For the empirical mass, I need to take the mass of iron Fe3O4. So 3 irons, 3 times 55.85, plus 4 oxygens, 4 times 16, give us 231.55 grams per mole. My grams per mole cancel. Now, with this calculation of multiplier, we can be really generous with rounding. This has to be a whole number. So even though you're going to plug this into your calculator and get 0.999, you're going to round that up. That's pretty much 1. And so this was our empirical formula. Our molecular formula is 1 times our empirical formula, which means that it is exactly the same. And again, that's okay. It's okay to have an identical empirical and molecular formula. What's not okay is you cannot have an empirical formula or a molecular formula that has fractional or decimal subscripts. And that's why we take on these steps that we did to kind of prevent that. All right. Any questions about this example in particular? All right, so let's close out this review session by doing one last problem. We have phosphorus. Phosphorus burns in oxygen to create a pure white light and a chemical compound that is 43.64% phosphorus and 56.36% oxygen. The molar mass of this substance is 284 grams per mole. Based on these data, the empirical formula is Planck, and the molecular formula is blank. All I'm looking for in those two spots is a chemical formula. You're not going to be able to format it, so just put it in like what's shown on the board. If you get P2O3, just write it in as capital P2, capital O3. I'll give you a few minutes to work on this, and then we'll take it from there. So let's kind of go through the whole thing and get in the right sense here. So we're going to do exactly like we have been. So 43.64% phosphorus gets turned into 43.64 grams of phosphorus. 56.36% oxygen gets turned into 56.36 grams of oxygen. Now, if you don't have your periodic tables on hand, this can be the part that's a little bit more difficult. You need to turn the grams of phosphorus into moles. 1 mole of phosphorus is 30.97 grams. I'll get your grams of phosphorus cancel and leave you your moles. Oxygen we've worked with several times, and if you don't have this particular molar mass memorized by the end of the semester, I'm not sure what to tell you. But 16 grams of oxygen in every mole. And so if I do the calculations, 43.64 divided by 30.97 will give me 1.409 moles of phosphorus. 56.36 divided by 16 will give me 3.523 moles of oxygen. Once again, the values here are not easily determined. So we're going to divide by the lower. So if we do that, we get 1 phosphorus and 2.5 oxygen, which means we're going to need to multiply by 2 to get rid of the half. So that means we're going to have 2 phosphorus, and 2.5 times 2 is 5 oxygen. The empirical formula here is going to be P2O5. So walking around the room, most of you were at least at this stage, which is a good sign. That means that you understand kind of the construction here. And as far as the lab that you're about to do goes, that's going to be a really important part, because as you get into that empirical formula lab, all you have to do in that lab is the same thing. Take your masses, convert them into moles, compare the moles against each other, determine the empirical formula of the substance that you're making. Now for the second part here, we got to do that multiplier business again. And so the multiplier here is going to be equal to 284 grams per mole, divided by whatever the mass of P2O5 is. 2 times 30.97 for phosphorus, plus 5 times 16 for oxygen gives 141.94 grams per mole. So if I divide that into 284, I get a multiplier of 2. So my molecular formula is equal to 2 times my empirical formula, P2O5, which means it would be P4O10. I just multiply that 2 by both of the subscripts. So P4O10 should be what I write into that last column there. All right, any questions with this particular example now that we've walked through it? All right, so before we transition into chapter 3, I forgot to do this on Friday. I want to make sure that you actually get a chance to earn these easy points. So answer this question specifically with regard to empirical and molecular formulas. How do you feel about your level of confidence in empirical and molecular formula calculations? All right, so we're moving now then into chapter 3. Now, chapter 3 is kind of a unique look on things on its own. So if you remember back to before we started breaking out our calculators in chapter 2, we started with this idea of the atom, and we broke it down into protons and neutrons and electrons. And we spent the most of chapter 2 talking about those protons and neutrons inside of that nucleus. We kind of said, yeah, those electrons are there. J.J. Thomson and Millikan kind of helped us to describe them. We'll leave that for later. Well, now we've arrived at later. And so most of what we are going to talk about in chapter 3 is going to focus on electrons and all the wacky things that electrons do to help us to understand the chemistry of an element and of the compounds a little bit better. So before we get into that fully, we need to have an understanding of just something known as the electromagnetic spectrum. What the electromagnetic spectrum is we have here a representation of all forms of radiant energy. So any form of wave-like energy that exists can be described using the electromagnetic spectrum. And they cover things like gamma rays, very, very high energy forms of light that have extremely high frequencies, extremely low wavelengths, and extremely large energies. These are the kinds of things that we see in outer space, that we see with high radioactive substances. And then way on the other side of the spectrum, we have radio waves. Now, there are probably radio waves going through this room right now. And we don't worry a lick about it because they are very long phase. They have very large wavelengths measured in the meters and tens and hundreds of meters. And they are very low energy. But we know they exist because, well, we've got a radio station not that far from here. It broadcasts in all directions. And all you need is a transmitter, and you can pick up that signal and start listening to what they're putting through that airwave. And for that matter, television works in the same kind of manner as well. at least that which is broadcast and can be received through an antenna. We don't worry about those. The energy is so low, it has no negative impact on our body systems. And here in the middle, this little tiny band here, from 400 nanometers to 750 nanometers in wavelength, this is visible light. This is the light we can actually see and detect with our eyes. So out of this great spectrum of all of these different wavelengths and frequencies, this little tiny rainbow band right here in the middle is all we can actually detect, at least with our own eyes. Now, with other kinds of detecting equipment, sure, we can expand out into the ultraviolet, we can expand out into the infrared. But on its own, not a whole lot we can do. When we describe the forms of energy that exist on the electromagnetic spectrum, what we are ultimately talking about are waves. And we can describe waves through a number of different kinds of descriptions. We can describe waves in terms of their wavelength. That is, how far is it from one wavelength up to another? So if I want to look at and describe the difference between this point and this point, or even valley to valley, that wavelength would be exactly the same. One thing about electromagnetic light, wave particle or wave theory, if we are looking at a standing wave, the wavelength is consistent. So we can see that wave A here has a relatively long wavelength. Wave B here has a relatively short wavelength. The distance between wave and wave is identical, but shorter. Now we can relate these two to each other using something called C. C would be representative of something called the speed of light. All light travels at that particular speed, just somewhere short of 300 million meters per second. And so what that tells us is that there is a relationship, an inverse relationship, between the frequency of light, that is, if I am standing in one spot and I'm staring at the waves as they go past me, how many waves am I going to count in a given second? And its wavelength. Obviously, the longer the wave is, the fewer wavelengths I'm going to count because all the waves are traveling at the exact same speed. So the longer the wavelength is, the smaller the frequency is going to be. The shorter the wavelength, the more I'm going to observe in that given amount of time, the higher the frequency is going to be. And we can tie the three ideas together, wavelength, frequency, and the speed of light, using this equation, where lambda, that funny looking T on its side, represents the wavelength of the light. C represents the speed of the light. And the Greek letter nu, that kind of fancy looking V, represents the frequency of the light. Now the common units for speed of light, it would be meters per second. Wavelength, its base unit would be meters. Although, depending upon the type of wave we're talking about, we might transition that into nanometers or picometers or femtometers, depending upon just how short that wavelength is. And frequency is given to us in reciprocal seconds, 1 over s. Or you may be more familiar with the term hertz, Hz. And again, where you've heard that term before is, again, radio. Usually when a radio signal broadcasts its station identification, that station identification is its frequency. Laser 91.1 broadcasts at a frequency of 91.1 megahertz. And so again, we use those big metric terms to help us to define quantity here. So FM signals are usually raised in megahertz, which would be millions of reciprocal seconds. AM signals are usually in kilohertz, thousands of reciprocal seconds. So this here represents just about as much calculation as we're going to get into in this particular chapter. This, and there's one concept after this about relating energy and frequency that we'll talk about shortly. What is the frequency of light associated with a wavelength of 640 nanometers? How much energy does this light wave contain? Well, we'll need another equation to help us with that. But if we start with this particular idea, we know that based on the equation, the speed of light is equal to the wavelength of light multiplied by its frequency. So 2.998 times 10 to the 8th meters per second is equal to the wavelength, 640 nanometers. Now we're going to have to turn that nanometers into meters. This is where our knowledge of metric prefixes is going to help us. And we're going to actually cheat it a little bit. And what do I mean by cheat it? Well, the easiest way to convert is to just use that number off of the table. And we're just going to use that in our scientific notation. So we're going to present this wavelength in an improper scientific notation. So 640 times 10 to the negative 9th meters. Why that conversion? Because every nanometer is 10 to the negative 9th meters. So we're just going to tack that on to our measurements. Now, when you go to put it in your calculator will autocorrect the improper scientific notation, put it in correct terms. It'll turn that into 6.4 times 10 to the negative 7th. It'll do that automatically for you. So the reason we do it this way, save us a little bit of time, save us from an accidental calculation mistake. Multiply it by the frequency. So to get it, I'm going to need to divide each side by 640 times 10 to the negative 9th meters. And so the meters will end up canceling out. I'll be left with reciprocal seconds for my frequency, 2.998 times 10 to the 8th, divided by 640 times 10 to the negative 9th. Do 3 significant figures. 4.68 times 10 to the 14th reciprocal seconds. Now, if you did not get that number when you put it into your calculator, one thing that you might want to check, make sure that you are using the scientific notation button on your calculator and not just simply typing in times 10 to the 9th when you put in that unit in the denominator. If you did that, then you probably got something more along the lines of 10 to the 1st, 10 to the 0th, something along there. Because you made a mistake in that. So, depending on your calculator, there's probably 1 or 2 buttons on there for scientific notation. Again, if you're having trouble with that, I'll be happy to show you how to use scientific notation on your particular calculator. For mine's a Casio. It's got this exponent button here that I can use to directly put in scientific notation instead of having to type in times 10 carat, whatever the exponent is. Now, to answer the second question, we're going to need more information. Specifically, we're going to need the information about the relationship between energy and the frequency of light. And that gets into something called quantization, which we'll talk about in just a minute. Before we go there, though, let's talk about one thing that was going on in that time era, right around when all of this started to kind of fall apart. So if you remember from that history of atomic theory video that I had you watch, the history of atomic theory was kind of constant up until about the 1800s. Then we had the Dalton postulates about just general atomic theory. And then toward the end of that century, we started to get into the work of J.J. Thomson and the others. Well, that period of time for about 40 years, between 1897 and about 1937, that 40-year time window was a massive revolution in the world of science and physics. Lots of stuff happened all at the same time. We had a big technology boom, and it brought about a whole bunch of change all at once. One of the things that was mysterious to the physicists of the time was this. Now, we all know what happens when we take light and hold it up to a glass prism. Light bends inside of that prism, it breaks apart into the colors of the rainbow. We haven't done it ourselves. We've certainly seen the album cover of Dark Side of the Moon by Pink Floyd. It's the same thing. But here's what was interesting. They started doing that in the laboratory, and if they looked closely enough, they started to see that if they did that with sunlight, they weren't getting that beautiful continuous spectrum. They were getting this spectrum with a whole bunch of black lines in it. And they said to themselves, hey, that's kind of weird. What's this all about? So they started to do some more investigation. And when they started to investigate individual atoms, they found that individual atoms also had similar kinds of difficulties. Depending upon how they were looking at it, they would either find that they would have a completely dark spectrum for an atom with just these very few bright lines in it. Or they'd have this continuous spectrum with a very few dark lines in it. And what was even more interesting is that when you put those two spectra right on top of each other, places where you had those bright lines matched up with the exact same wavelengths of where the dark lines were in the other spectrum. Point by point. And so this begged several questions, not the least of which was why? And so we're going to leave today with you trying to answer that question, why? Try to come up with an explanation for why those bright lines occurred and appeared as dark lines in other spectra. Why specifically those wavelengths? Why were they the same but in opposite places? Why weren't atomic spectra continuous? So type out your answer here. And then when you go to do the assignment tonight, we didn't get quite through everything here. You might want to watch that second video. That second video is going to put into place the things that you're missing out of this last part. So go through that information. If it's still fuzzy after you get through that assignment, I'm going to put a confidence meter in the assignment itself. Tell me that it's still fuzzy. Type out in the feedback box what you're still lacking. We'll talk about it first thing on Wednesday. If I don't hear from you, I'm going to assume everything's okay. And we're going to go straight into the photoelectric effect in the Bohr model right off the bat on Wednesday. So at this point, I don't need a correct answer in this box. I just need to know where your head is. So give me your best explanation. Doesn't matter if it's right or wrong. And once you have that, you're free to go for the day. And I'll see you on Wednesday.